Hello everyone. Okay, good afternoon. Right. So we continue from yesterday. So I hope we can finish this chapter by today. And so for tomorrow, we will do a revision, right? For paper one. So I will compile all the objective question for the trial. So we're doing the revision by chapter. Okay. So before I start the class tomorrow, so I will send you the soft copy. So maybe if you want to do it first, then you can read first and we will discuss. Okay. So today we continue with the photoelectric effect, right? So yesterday we already see what does it mean by wave particle duality, right? That wave also is actually can act as a wave and at the same time also as a particle. Okay, so they can act like a wave. Okay, they can be diffracted, be reflected by be refract, right? Okay, and also at the same time they act as a particle also, right? They in a packet, right? So I already told you that the light is in packet that we call it as a photon. Okay, the photon. Okay, the energy is packed. The light energy is being packed in a packet. And we call it as a photon, right? And we already learned how to calculate the energy for the photon, right? E is equals to hf. Okay, and we also already calculate the power, right? The power, right? The work, right? Yesterday, okay, and also the formula, okay, for work and also the power. Okay, so E is equals to hc lambda. So I teach you how they derive this formula. Right, so now we continue with the photoelectric effect. Okay, so when a metal surface is illuminated by a beam of light at certain frequency, okay, so electron can be emitted from the metal. Okay, so this phenomenon is known as a photoelectric effect. Okay, so a light, let's say if you give a light, okay, to the any surface, right? So in a certain frequency. Okay, so you already know there will have a energy, right? Because E is equals to hf, right? So means there will be energy. The light will contain the energy. So this energy, okay, let's say is emitted, okay, to the metal of surface. Okay, then the electron can be emitted from the metal. So is this the same as the concept of the thermionic emission? If you still remember, okay, for the chapter 6, chapter 5, right? The semiconductor, right? In the CRO, right? So remember when you heat the metal, then if the electron gain enough energy, they will emitted by from the metal. So that one is they give heat energy. Okay, but for this one is a light. Okay, so it's a different thing. So when a metal surface is illuminated by a beam of light, certain frequency means they got energy because E is equals to hf, right? So they got certain energy, then I strike it to the metal surface. Then if the energy is enough, okay, the electron will come out from the metal, right? Okay. So next, right, the characteristic of the photoelectric effect. So we already know what is a photoelectric effect. So the characteristic of photoelectric effect can be studied, okay, by arranging a photocell in circuit as shown in figure 7.7. Right. So the first part is this: when a light sensitive metal surface, okay, we call it as a cathode, right, is illuminated with a certain light beam, okay, electron will be emitted from the metal surface. So these electrons are called as photoelectron. Okay, so let's say you have a light, all right, and you just strike it to the metal surface, to the light sensitive metal surface. So example as a cathode, all right, and the energy is enough, okay, for the electron, okay, then it will emitted, okay, out from the metal surface. Then the electron that coming out from the metal surface, we call it as the photoelectron. Okay, so mean photo is light, right? Usually the photo means light, so means the light. Okay, the light that make the electrons come out from the metal surface. Okay, then the number two is says, okay, so this is the light source. Okay, you put it in the illuminated surface, the light sensitive metal. Okay, then if the energy enough, then the electron will come out. So this electron we call it as the photoelectron. So the emitted photoelectron are attracted to the anode which has a positive potential. So we put the anode here. Okay, we put the anode here. This is the cathode, right? This is the cathode. Of course, this have to be a cathode because the cathode means the negative. So there we have the electrons there, right? So this is the anode. So it will be attracted because they have a different charge, right? So the emitted photoelectrons are attracted to the anode, which has a positive potential, right? Then the movement of the photoelectron, okay, from the cathode to the anode produce a current inside the circuit. The milliammeter shows the value of the current. Okay, so now we already know if we strike out the light through the light sensitive metal and is enough, the frequency is enough, mean the energy is enough because E is equals to HF. Okay, and H is the constant, F is the frequency, so it depend on the frequency. Okay, the energy will depend on the frequency. Okay, so if the frequency enough, okay, means you have enough energy, so the electron will come out from the metal surface. So this electron that come out from the metal surface, we call it as the photoelectron. Okay, so since we already know this is the cathode, right? Because this one we emitted the electron, so that's why we have to put this one as a cathode, right? Then this part is the anode. So you already know different charge will be attracted to each other. So the negative will be attracted to the positive. Okay. Then after that, right, the movement of the photoelectron, the movement of the electron from this to here, okay, that will produce the current. Okay, all right. Then okay, you can see the direction. All right. Then you will say, but teacher, the milliammeter shows the opposite, right? It should be same as because your current, the flow of electron from here to here, right? But yours milliammeter shows the opposite way. Okay, so this one is actually same as I think we learn in the chapter, I think the semiconductor. No, the remember we learned for the induced current, right? Yeah, the induced current. So actually the flow of electron is actually opposite from the terminal, the battery. So they say if your if your the electron moves from here to here, okay, means your direction of the milliammeter, okay, will be moved from the opposite way. Okay. So it will move this way. So that's why your milliammeter move this way. It's just like your galvanometer for induced current, right? Okay, for induced current, the direction of they say you have a solenoid, right? You have a solenoid, then you label the current, right? Based from your by using your right grip hand rule too, right? Then after that you can see the flow electron, but actually the direction is opposite way. So it's the same as this one also. Okay, so the electron move this way. Okay, but your milliammeter will show in the opposite way. Okay, so this is the to show that the photoelectric effect, right? So if let's say then how does this one prove the photoelectric effect? Because you know that this one they have a gap. So when they have a gap, means actually the current will not flow. But then how does it flow? So mean there must be something that been transmit from the cathode to the anode that makes the current flows in this circuit. So mean there must be the electron that from cathode to anode. So mean the metal must release the electron so it can be moved here. Okay, but then we have to give some energy lah. Okay, but this one we use a light energy. Okay, it's different from the thermionic emission. Thermionic emission we use a heat energy. Okay, it's different. This one is a light energy. So if light energy is photoelectric effect, if the heat energy, okay, for the CRO, okay, that one is actually thermionic emission. We use a heat. That's why we call it as a thermionic. Okay. So formulas such as E is equals to HF and lambda is equals to H over P. P is what? P is the momentum. There is mv, right? Involve Planck constant H. How can value of this constant H be being determined in the laboratory? Okay, so this one is actually we have to do it by this from the experiment. Okay, but we don't have the potentiometer. We don't have potentiometer is actually to measure the potential difference, okay, between the voltmeter and also the ammeter. So you can see the red one connecting to the voltmeter, the black one connecting to the milliammeter. So this one is actually to measure the potential difference between these two. Okay, potentiometer. Alright, so that part is the activation voltage VA can be obtained through the V-intercept from the I against V as shown in figure 7.9. Okay, so this is actually the I against V graph. Okay, after you doing this experiment, okay, so we have to draw the I against V graph. Okay, so this is the graph that we got. So VA is actually the activation voltage, right? So means the what is the voltage needed, right? The minimum voltage needed. Okay, can be obtained through a V-intercept from the graph of I against V. Okay, and the activation voltage VA has a linear relationship with 1 over lambda. Okay, so 1 over lambda. Okay, as shown in figure 7.10, right? So this is I against V graph. Okay, and this one is the, let's say, the activation voltage against 1 over lambda. So you can get a linear relationship. Okay, and the gradient of VA against 1 over lambda m is equals to HC over E. HC over E. Okay, therefore the value of the Planck's constant can be determined by it is this one. Okay, can be determined by determined as ME over C. Okay, what is E? E is actually the charge of electron. Okay, so 1.6 times 10 power of negative 19. So how do we get the Planck constant? Okay, so the Planck constant can be used this formula. That is M is the actually the mass. Okay, the mass of the electron. E is actually the charge of the electron, and C is the speed of light. Okay, so you can get the H. Okay, so what you need to remember is actually the graph, of course. Okay, what type of graph? If we draw the I against V graph, okay, and what do you get? Do you get the intercept of intercept of X? We call it as a activation voltage. Okay, and let's say the activation voltage against 1 over lambda. Okay, so you will get the linear relationship. The gradient is actually equals to the Planck constant. Okay, therefore the value of Planck constant can be determined by using this formula. So SME is equals to C. Okay, so maybe you have to remember, because I cannot see this formula in the formula that they give in front. The one that I see is equals to HF, right? And also the another part HC over lambda also is not given. Okay, that one you have to derive on your own. Okay, because you use a concept V is equals to F lambda. Okay, they just give you the formula, I mean the basic formula, then you need have to derive it on your own. Okay, so this one maybe you need to remember, and also another one HC over lambda. Okay. All right, so this is the two type of graph. So you see here, every time they mention about the word gradient, there must be a triangle. So this is the triangle. Okay, who knows? Maybe paper 2, right? Paper 3 already passed, right? But maybe paper 2 they will ask you the gradient, and I give you some tips, right, in the group. Okay, but it's in Malay. But let's say you cannot understand, right, certain words in Malay because of the terms. You can ask me, so I will translate it for you. Okay, but that one is only a tips. Don't depend on it 100%. Please don't. Okay, don't, like, I will just only read this topic. Please don't have to study all of it. Okay, even when we discuss the question after this, okay, starting from tomorrow, okay, I will discuss all. I will not just focus on the topic. So but they say if you read, then maybe that time you that part maybe you can, read, like maybe 2 3 times, but you have to know all of it. Okay, don't depend on that. All right, so the next part is the characteristic of the photoelectric effect. So the photoelectric effect occurs when the light strikes the surface of metal. So this one we already know, right? The electrons in the metal absorb energy from the light and escape from the metal surface. It's just same concept as the thermionic emission. For the thermionic emission is absorb the heat energy. Then when it gain enough energy, it will come out from the metal surface. The electron will come out, right? So according to the classical theory, light in wave form is a spectrum with a continuous energy. Okay, that what is the classical theory said. That is actually is a continuous. Okay, it's a continuous energy, right? You remember the transition of light, right? The Roy GB, you can see it's like a continuous form. Okay, and the photoelectric effect should be able to occur at any light wave frequency. Okay, bright light which has high energy, okay, should be able to emit electrons quickly. Okay, then dim light has low energy. Okay, then the electron needs a longer time to absorb enough energy to escape from the metal surface. However, the result of the photoelectric effect experiment shows that the emission of photoelectron only apply to light wave with frequency that exceed a certain value without being affected by the intensity of light. Okay, so if you learn from the classical theory, okay, it says that if means the bright light mean it has a high intensity. Mean of course they have light. The energy is higher, right? The light energy is higher. Okay, so means the electron we get enough energy to come out from the electron. Okay, but the light is dim. Okay, means the light energy is low. So mean it will takes time for the electron to come out from the metal. That is what the classical theory said. Okay, but however, when we do the photoelectric experiment, okay, it shows that the emission of photoelectrons, okay, the emission of the photoelectrons only applied to light wave with frequency that exceed a certain value without being affected by the intensity of light. Okay, so now for the emission of the photoelectrons, okay, based from the experiment for the photoelectric effect, it depend on the frequency. Okay, so it doesn't depend on the intensity of light, whether the light is bright or dark, or bright or dark, bright or dim. Okay, it doesn't influence the electron. Okay, the photoelectrons. Okay, so they only depends on the frequency, right? So if the light is can exceed the frequencies, right? Certain frequency, then the electron will gain enough energy, then it will emitted the photoelectrons. So the photoelectron also emitted instantaneously at those light frequency, even at the low light intensity. Even there is low light intensity, but the frequency is higher, right? But the frequency of light is higher, the photoelectron can also be emitted from the metal surface. Okay, so this one is different from the classical theory. Classical theory say it mean if the light intensity higher, of course the energy of light also higher, right? Then the if higher, that mean there's enough, there's easy for the metal surface, right, to emit the photoelectrons. Okay, but that is the classical theory said. But all right, when we do the experiment of photoelectric effects, even like let's say we give the bright, right, for the bright light to the metal surface, okay, but the frequency is not enough, okay, but the frequency is not enough, the photon electron will not be emitted out, okay. So but if they say low intensity means the light is dim but the frequency is high, okay, you can still, the photoelectron still can come out from the metal surface, okay. So this one is actually depend on the frequency. That's why E is equals to HF, right? So it depends on the frequency. Okay. So this one is said the higher the frequency of the photon of light, the higher the kinetic energy, right? So the higher the frequency of the photon, okay, the higher the kinetic energy. So this one we learned yesterday. The frequency means how how frequent, right? The vibration, okay? The vibration of the electron inside, the vibration of electron there. So when it vibrate very faster means the kinetic energy also will be higher, okay? So the higher the frequency, the higher the kinetic energy of photoelectron emitted from the metal surface. The minimum frequency of light needed for a metal to emit electrons is known as threshold frequency. So this is the minimum frequency. All right, the minimum frequency for the metal, okay, for the metal to emit the photoelectron. Okay, let's say if I have a metal, okay, let's say this is a metal, then my the light frequency, let's say the frequency here is 7 times, let's say lah, okay, power of 2, 10 power of 2 hertz, right? So this is the minimum. So they say if I strike, the light strike to the metal and it has a frequency of 7 times 10 power of 2, so it's already have enough of energy to emit the photoelectrons, right? Okay, so the minimum frequency that it needs, this one is we call it as the threshold frequency. Okay, the minimum, right? So let's say if you give more than 7 times 10 power of 2, of course, right, the electron will be emitted out. Okay, then the kinetic energy of the photoelectron does not depend on the intensity of light. This we already discussed. Okay, so whether you give a bright, okay, the bright light to the metal, okay, but the frequency is low, okay, so it will still not emitted the photoelectrons. But if you give even you give a dim light but high frequency to the metal, okay, then the metal will gain enough energy, then it can come out. So based to this experiment, this formula, sorry. An increase of the light intensity does not produce photoelectron with higher kinetic energy. So the base thing is actually the one that they want to state here. Okay, the emitted of the electron, okay, the photoelectron is not influenced by the intensity of light. It's influenced by the frequency of light. Okay, so you can just refer from the formula E is equals to HF, right? Okay. Then another part, number 4, it says photoelectrons are emitted instantaneously when a metal surface is illuminated by light. Okay, so it will come out instantly. Okay, so the emission of electron from a metal surface by thermionic emission may take some time. So this is actually the difference lah. Okay, for thermionic emission, the one that we learn in the CRO, right? Okay, we learn about the characteristic of the electron. Remember, the electron travel in the straight line. Okay, then when you hit the Maltese cross, okay, you can see it form a cross. Okay, and the cross and the shadow can be deflected by the magnetic field, right? And remember that one. Okay, so the thermionic emission, okay, it takes some time. It takes some time because they use a heat, right? But in the emission of the electron, or we call it as a photoelectric effect, okay? So this one, the emission of the electron from a metal surface by photoelectric effect is instantaneous. So that is the difference between these two, okay? And also of course lah, the source of energy that they use. Okay, thermionic they use heat, while the electric effect they use a light. Okay, so the threshold frequency F0 is the minimum frequency required to produce the photoelectric effect on a metal. So photoelectric effect is what? Photoelectric effect is when the electron come out from the metal. Okay, that we call it as the photoelectric effect by using a light. Okay, so that is photoelectric effect. So I hope you can understand the photoelectric effect is actually when they give a light, okay, to the metal, okay, that the metal surface. Then when the light has enough frequency, okay, and it hits the metal, then the metal can emit the electron, then the electron we call it as a photoelectron. Then the moment that the process when the electron come out, okay, from the metal, we call it as the photoelectric effect. Okay, and remember, it's not depend on the light intensity, it depend on the frequency based from this formula. E is equals to hf, right? Okay, the next part, the last one, okay, is the Einstein photoelectric theory. So this is the last part. Okay, so I think that 5M got one more subtopic, then the rest of it 5S and 5K already finished. So we can start our discussion. Okay. So Einstein photoelectric theory. So in 1905, okay, Albert Einstein introduced a photoelectric theory that successfully explained all the characteristics of a photoelectric effect in related experiment. Okay, so he was awarded the Nobel Prize in 1921 for this achievement. So this theory is named as the Einstein photoelectric theory. Okay, that's a usual because let's say that if the scientists found a new theory, right, they will use their own name. Okay, but however, what I know, I heard lah, I'm not sure whether it's true or not. Okay, that's a rumor said. Now they are trying to prove. I think I'm not sure whether Einstein or Newton theory, there is actually some of it is not correct. Okay, but they are trying to prove it. Okay, but for you, okay, for our part, okay, we just follow that one. This the one that you learn. Okay, I heard that say now they are proving that actually some of it the theory is not correct. Okay, that one we just say just I mean I just want to tell you lah, right? I just want to share. Okay, there's now there being a research, right, to show that some of the theory is actually not correct. Okay, but it's okay, let them do it. Okay, so we are focusing now. They just like I just want you to let you know lah. Kan mana tahu tiba-tiba when you go to the university then they say whatever you learn in school is actually no wrong, but actually like this one, okay. And it's just a story since we already almost finished, right? When you go to the university, right? When I went to the university, when on the physics, I think the mechanical physics, okay, that subject. So we already learned actually Newton got three laws, right? The first law is inertia, second law is F is equals to ma, and the third law is actually action and reaction, right? So when the lecturer asks, so what is it, how many laws that Newton have? So of course we said three. Okay, that what we learn at school. But actually there's only one. Because the one law is come from the first law, like the initial laws. But then we derive it until three. Okay, then you have to use a calculus, like the integration, differentiation. So that one you will learn lah. Where if you are interested, okay, in learning physics. right? The mechanical, you will learn that one. Okay, so good luck. Okay, so Einstein photoelectric theory. So this is already okay. So this is actually why he got the Nobel Prize. Okay, so Einstein applied Max Planck ideas of energy quantum. Means the energy is in the form of packet. Okay, we call it as a photon. Okay, and he suggested that energy is carried by light particles called photons. Okay, and the energy of each photon is directly proportional to the frequency of light and can be determined by the following equation. So this is the one that we learned just before. E is equals to hf. So each quantum of light is a discrete packet of energy, right? So it's a discrete packet. It's in the packet. Okay, so the energy. So there are many energy packets in the beam of light that shines on the metal surface. Okay, let's say if I draw lah. Okay, if I draw, let's say this is the light. Okay, so means it's like a packet. We just assume it's like a packet of energy. So inside the light, okay, they got like a packet of energy. Okay, then when a photon arrives at metal surface, the photon energy, right? So E is equals to hf, right? So this photon energy will be absorbed by an electron in the metal. Okay, so this photon energy will be absorbed by the metal. Okay, then after that, the energy is used to release the electron from the metal. Then the extra energy will become the kinetic energy of the photoelectron. Okay, so let's see if I have a metal here. Okay, if I have a metal here, so this is a packet of energy that we call it as a photon. And this packet of energy, we can find the energy by using E is equals to HF. Okay, but let's say they got 5 of packet means you need to put 5 times HF lah. That is the total energy. Okay, so then this energy, the photon energy, okay, the energy from the photon will hit the metal of surface. But then you already know the energy cannot be destroyed. It only can change to another form, right? So when you hit the metal surface, this energy will be transferred to the electron. Okay, it will be transferred to the electron. Then the electron, if the frequency is enough, okay, remember it depends on the frequency, right? If the frequency is enough, the electron can emit it, okay, from the metal surface. Okay, then the extra energy that given by the photon energy, okay, then we use it to move. Once it come out, the electrons come out from the metal, we call it the electron as the photoelectron. Okay, so remember, if the once the electron come out from the metal, the electron that come out, we call it as a photoelectron. Okay, so how does the photoelectron move? Okay, so they move by using the extra energy that been given by the photon energy just now that hit the surface. Okay, so usually the electrons on the metal surface will acquire maximum kinetic energy compared the electron inside the metal. So it says here that the electron on the metal surface, okay, will on the metal surface here will acquire a maximum kinetic energy if you compare to the electron inside the metal. So mean in the electron that on the surface on the metal here, they will move with the maximum kinetic energy compared the electron, okay, inside of the metal here. Okay. So from the electrons on the metal surface, so the photon energy is actually equals to what? Is actually equals to the minimum energy required to release a photoelectron. Okay, and plus with the maximum kinetic energy of the photoelectrons. Okay, so the photo energy that strike, okay, to the metal surface is equals to the energy that being used, okay, to emit the photoelectron. Okay, because they only need minimum, remember they emit instantaneously. Okay, they don't have in as long they can overcome the threshold frequency, the frequency that hits the metal, okay, from the light is more than the threshold frequency. Okay, it will emit the photoelectron, right? So the minimum energy required to release a photoelectrons and plus with the maximum kinetic energy of photoelectrons. So remember the extra energy that been given by the photon we turn into the kinetic energy for the photoelectrons to move. Okay, to move out. Of course they have to move. They move, when they move, of course they need energy. Okay, so if you add these two, you will get the total of photon energy that being applied to the surface. So this is W. W means it's a work, yeah, it's a work, right? Work is also in joule. Okay, and this is the kinetic energy. Okay, so after that, the kinetic energy, okay, the maximum kinetic energy is equals to HF minus W. Okay, this one they turn the change the E to HF. Okay, the W, okay, is a W. Okay, still use a W. And K max is the kinetic energy, that is half mv square max, the maximum velocity. Because the mass of course cannot change. The mass of electron always 1.6 times 10 power of negative 19, right? So the mass is a constant. So the one that will be a maximum is actually the velocity. Okay. So how you want to find the maximum kinetic energy of photoelectron? So you just minus the photon of energy with the minimum energy that need, okay, to make the photoelectrons coming out from the metal. So instant photoelectric is in accordance with the principle of conservation of energy. So remember the energy cannot be destroyed, it only can change form. So it's obey. Okay, so the energy, where's the photon of energy of photons go, right? So it changed to kinetic energy, and also it used to make the photoelectrons come out from the uh, metal surface. Right? So it obey the principle of conservation of energy. So at the threshold frequency F0, photoelectrons are emitted without any kinetic energy. So let's say threshold is the minimum frequency. So if you the minimum, I just give you example just now, right? Like 6 times okay, like 7 times 10 power of 2. That is a threshold. So if you give only 7, let's say the frequency of the light is only like 7 times 10 power of 2, only enough for the threshold frequency. Means the energy is only enough to make the photoelectrons come out from the metal surface, right? But in order for the photoelectron to move, they need more energy. Okay, but the one that you apply is only enough for it to come out from the metal surface. Okay, so it said here the half mv square is equals to 0 because there is no kinetic energy. So then 0 is equals to hf0. This is actually the threshold frequency minus w. Okay, so w is equals to hfo. Okay, then after that substitute w is equals to hfo inside w here. Okay, this one. Okay, we using copy back this one. So now your W is HFO, means the Planck constant times the threshold frequency. So if you asking teacher, how do we calculate the value of W? E we already know by using HF, right? K max means the kinetic energy maximum, we already know, half mv square. But then how we calculate the W? You cannot use Fs because that one is for the force. Right, W is equals to Fs. There have to be a displacement. There have to be, the force, right? That one is cannot be used. That one is for the force. But how do we find for the electrons? So the W is actually HFO, the Planck constant times with the frequency threshold. The frequency threshold is the minimum frequency for the light, okay? The minimum frequency that come from the light, okay, when it hit the metal surface, then then the electron can come out. Okay, but then only can come out, cannot move in a maximum kinetic energy. The kinetic energy is 0, means doesn't move. Okay, so W is HFO. Okay, then after that we just factorize it. Okay, so your F is the frequency for the from the energy of photon. Okay, then minus HFO. Okay, then this one just factor, then we will get this equation. Okay, so if some of you ask me what is the formula for W, is HFO. Okay, but then you can derive it. Okay, if they want to find the kinetic energy, if they give you the threshold frequency, okay, and then you can use this formula. All right, so this is the derivation. Okay, I think this is the last, yeah, the last part. Then after that, okay. Oh no, still have another one. Okay, never mind, we still have time. Okay, work function and threshold frequency for photoelectric effect. So this one, the minimum energy required for the photoelectron to emitted from the metal surface is known as the work function. Okay, just now is the minimum frequency, right? Minimum frequency for the metal surface to make sure that the photoelectron come out from the metal surface. That one we call it as a threshold frequency. But if the minimum energy, okay, what is the minimum energy for the metal surface, okay, that so it can emit the photoelectron, we call it as the work function. So the minimum frequency for a light photon to produce photoelectric effect is called as a threshold frequency. So the energy, minimum energy, we call it as a work function. The minimum frequency is a threshold frequency. So the relationship between the maximum kinetic energy of photoelectron Kmax and the light frequency f is shown by the diagram 7.12. So the graph is a straight line with the positive gradient not passing through the origin. So the threshold f0 is the value of the intercept of the frequency axis. Okay, so you already know, in order for the metal surface to emit the electrons, they will have to reach a certain frequency. If the frequency, okay, you cannot reach the certain frequency, then there will be no electron emitted, okay, from the metal. Okay, so starting from now, from zero, of course, no frequency, zero frequency, then how come the electron can come out from the metal? Because you don't apply any frequency there. You don't give any energy you don't give any energy to the metal. Okay, but then you keep increase the frequency. Okay, you keep increase the frequency. Maybe you use a different light, or maybe you increase the intensity. No, not intensity of light. You increase the frequency of light. Okay, but then when after certain frequencies, all right, you can see there is a photoelectric effect. What is a photoelectric effect? Means you can see the electron start coming out from the electron. Okay, how do we know, teacher? How do we know the photoelectric effect? Remember the experiment that we done? That we have? No, we didn't. I mean that we discussed just now. The electron come out from the metal, right? And it hits the anode. Then they connected to the milliammeter. They show the readings, right? Okay. So when it start to give a reading in the milliammeter. Then you already know, yeah, photoelectric already occur. Once the moment the milliammeter start to move, that one, oh, okay, the photoelectric effect is occur now. So that is the threshold frequency. So mean you take, okay, let's say you adjust the frequency of light. So maybe first you put one, okay, or so still the millimeter still show no reading. Okay, then you put 2 hertz, still no reading. Okay, then later you put 3 hertz. So when you put 3 hertz, then suddenly your millimeter, okay, is starting to deflect. Okay, so then you know that 3 hertz is actually the threshold frequency. Okay, then after that you keep increase. Okay, you keep increase the value of frequency. Then you can see the increase of the reading of the millimeter. So means the photoelectric effect, okay, keep increasing also. This is a number of photoelectric effect. Okay, then after that, the relationship between work function and the threshold frequency of a metal can be determined by W is equals to HFO. Okay, so the work that being done, okay, to make the electron coming out from the metal, okay, we call it as the um, work, okay, work done if not mistaken, yeah, work function. Okay, So then after that, the photoelectron will acquire kinetic energy when light at frequency exceed threshold frequency. So at this moment, the FO mean this one, the kinetic energy is zero. Okay, because I just told you just now, the energy is only enough to take out the electron from the metal surface, but then it need more energy to make sure that the photoelectron can move. Okay, so it says here, that's why we, if you increase, then you can see, okay, that's a movement there. So the photoelectrons will acquire kinetic energy when light frequency exceed threshold frequency. The higher the threshold frequency of the metal, the higher the work function, of course. Okay, so if your FO, let's say your FO is here. Okay, so means it needs more frequency, because from here to here, of course, you know the number is increasing, right? So let's say if I have a metal A and metal B, example. Okay, so means metal B will need more threshold frequency to make sure that the photoelectron come up from the metal. Okay, if you compare with A. So you need to know how to read the graph. Okay, and this means the minimum energy required for photoelectric effect to occur is higher. Okay, so mean at this part you need more energy, right? So if this one, let's say I take just now 3, right? 3 hertz. Okay, so let's say this is a 5 hertz. This is only the threshold frequency. Okay, so the moment for, let's say for A, the photoelectric effect occurs can already occur during the frequency 3 hertz. But for B, they need more time. Okay, like 5 hertz, then the photoelectric effect occur. Okay, then the electron come out from the metal surface. Okay, so it means, that it will need more energy. Okay, it will need more energy, okay, to make the photoelectron to move. Mean the kinetic energy, it needs more kinetic energy, because E is equals to HF, right? So the higher the frequency, the higher the energy. Okay, this means the minimum energy is higher. So different metal have different threshold frequency. So this is example. Let's say metal A, metal B, metal C. Okay, graph with same gradient. So the gradient actually equals to what? Okay, you already learned that one is I over lambda, right? I over lambda. So the gradient is same. So the graph of the K max against for different type of metal. So different type of metal, different type of threshold. Okay. Alright. So this is actually the experiment. Okay. You can just scan the QR code here to see. Right, and this is actually to prove the formula, and this is the equation example for the calculation. Okay, so I see the example 1 first. So a blue light with a frequency 6.67 times 10 power of 14 hertz is shown on a clean calcium metal surface. What is the maximum kinetic energy for photoelectron emitted? So what you do is you need to take out all the info given. Okay, the first one, you have to identify the problem. So the question asking you to find the K max, right? The K max, half MV max. And they have to be squared here, okay? All right, then you need to find this one. They give you work function of calcium. So when they said work function, you already know this one is the W is equals to HFO. Okay, how many work is done to the calcium to make the electron come up from the metal? Okay, and this Planck constant, this is H. Okay, so this one we already know. I already take out the formula, the frequency. Okay, frequency 6.67 times 10 power of 14. They give you here the frequency, the F, the work function W already given, the Planck constant also given in the question. So we use the formula E is equals to, remember, the conservation of energy The photon energy equals to the work function. The work function is actually the energy that you need to give to the metal surface so the photoelectron can come out. Okay, the minimum energy plus with the kinetic energy, the maximum kinetic energy. But for this, for the kinetic energy, for this one, make sure that the energy is higher than this one, because the kinetic energy only will be applied if the energy is enough for the work function here. Okay, they need to take out the photoelectron first. Then we think, okay, how to move it. Did we have enough energy? Okay, like that. So HF is a W plus K max. So you just substitute the value here. Okay, K max. Okay, then K max. So just substitute the value here. So if in the graph, so remember what is the value in this one? This is the F0, is F0. F0 means the FO, not F0, FO, okay? So the threshold frequency, the minimum frequency for the photoelectric effect to occur, right? So I think at that part also you just need to do the just a substitution. Okay, we will see this chapter for the exercise in the trial exam. We take out. Okay, we will start chapter 1 and chapter 2 tomorrow. Okay, all right. So this is the example of the calculation. So generating photoelectric current in a photo cell circuit. Okay, so what is the function? Okay, what is the application? Okay, why we need to learn for photoelectric current? So the photoelectric current we use in the photo cell circuit. So this is the figure 7.1. Okay, can I take some time because I would just want to finish it today? Okay, wait, I see first. Yeah. Okay, only some. I think we can finish. Give me like 4 or 5 minutes extra. Okay. So I can finish this chapter. So generating photoelectric current in the photocell circuit. Alright, so this is figure 7.15. Okay, a photocell circuit consisting of glass vacuum tube. Glass tube, it so means there is no air inside of it. So the semi-cylindrical cathode, okay, semi-cylindrical cathode is coated with the light sensitive metal. Of course, this one the electron will be emitted from here. So that's why that we have to use a cathode and we coated it with the light sensitive metal because we want when the light strike out to the metal, okay, the energy can be used to release the photoelectron. And connected to the negative terminal, of course, okay, we connected the negative plate to the cathode, okay, and the positive will be here, right? And then after that, the anode is a metal rod fixed at the axis at the semi-cylindrical cathode and connected to the to the positive terminal. Positive potential, mean terminal, so it's same lah. So when the photocell is illuminated by light, okay, so let's say we struck, okay, we just strike the light to the cathode, okay, the production of photoelectric effect. So we just use the photoelectric means when you struck the light into the cathode here, they will release the electron, okay, if the frequency enough, okay. Then the electron will be moved to the positive plate, okay. Then the current will flow from here to here, right? From here to here. But then the millimeter will show the opposite way, okay. So this is the what they use in the photos. If you use a photoelectric circuit, current in the photo cell circuit, they use a light, right? Then this is the comparison, okay. For if let's say if you use a plate, the cathode we use a caesium or we use a lithium, okay. So if you use a caesium as a cathode, right, the work function of the caesium is 2.15 eV. EV means the voltage. E is actually the number of the charge, okay, the charge of the electron. Okay, so EV, all right, and this one is 2.5. Okay, means the work function mean caesium, okay, they only they have a low energy, so they need a low energy compared to lithium to release the electron to do a photoelectric effect. So this one, they just need 2.14 eV, okay, to make sure that the photoelectric effect occur. That means the electron can come out. While for the lithium, they need 2.5 eV. Okay, so then the electron will come out, the photoelectric effect will occur. Then the threshold frequency. So you can see 5.16. 5.16 is already enough for the photoelectric effect to occur, or for the photoelectron to come out from the cathode. But for the lithium, they need 6.03, means they need much higher lah than the caesium. And the maximum wavelength to produce photoelectric current is 579. Okay, while the maximum wavelength to produce photoelectric current is 496, right? So on the whole, the higher the work function, the shorter the maximum wavelength. Okay, so if you need more frequency or you need more work, okay, W is actually what? HF 0, right? So the shorter the maximum wavelength, okay, required to produce the photoelectric current. Okay, so as the light intensity increase, the photoelectric current in the photocell circuit also increase, right? So that's the conclusion. And this is the application, right? So we use it in the LED lamps along the road which are powered by solar cell. This one I don't think we have, okay, in Malaysia. Okay, maybe I'm not sure. So far, I don't know. Okay, energy efficient, of course, right, and environmentally friendly, of course. Okay, and of course, is save cost. Okay, but then, of course, the photo cell is quite expensive also. Okay, but in the long term, it's like save cost, right? So in daylight, the photoelectric effect solar enables electrical energy to store in the battery. So it's same as the solar car, right? They absorb the light energy, okay, during the daytime. Then after at night, okay, they will use it, okay, during when there is no light intensity, not enough light intensity. Then they will use the energy, okay, inside the battery. At night, the LED lamp will light up with the power from the battery. Okay, and the non-complex solar power plant in the Sahara Desert. Of course, Sahara is actually a desert, right? Of course, they have a very light intensity is very high. So, of course, they can use a solar. Okay, and this station expected to be complete in 2020. I think already completed. And it's capable of producing 580 megawatt capacity for use by 1 million residents. Okay, so of course this one we save enough budget lah. Okay, and light detectors at the automatic door use infrared beam and photo cell as switch. When the light path is disturbed, the photoelectric current in photo cell circuit will be disconnected and the door will remain open. This one is like you go to the mall, right? When you go enter, then it will open, kan? And then after that, they say if you then you walk away from the door, then it will close. Okay, that one when you come near to the door, okay, you will be the light, right? You will close, right? You will like, I don't know what to say. Dia akan halang, okay, halang cahaya tu. Okay, so you halang cahaya tu, so dia photocell tak boleh detect cahaya tu. So it cannot detect the light because you dah halang cahaya tu. So then dia after that, okay, you'll be disconnected lah because the photocell doesn't have the current is not flowing anymore because you just like halang cahaya tu, then you cannot detect the light, then the current will be disconnected. Then the door will open. Okay, or the image sensor, okay, in the resolution camera, okay, this component uses convert to light and electrical signal which can be processed to form a digital image. And the operation of ISS, okay, depend on the source of electrical energy generated from a solar panel. Of course, we know that they don't have any power plant station here. So of course, they will use the solar energy to produce the electric. So this is actually the solar panels. Okay, right. That has a 33,000 solar cell. So this is the function actually. Okay, so we finished chapter 7. Now finish already syllabus from 5. All right, then tomorrow we will do paper 1. Okay, paper 1 and also paper 2. So I think I will give you by tonight. Okay, the paper 1. Okay, then I will discuss one by one, and at the same time we will do a revision. Okay, so maybe tomorrow I will do it at night. Okay, I will do it at night maybe. Okay, so I see you tomorrow night, 8:30, 9:30. Okay, so take care, everyone. Thank you for today, for coming to my class today. So see you tomorrow night. Okay, take care, everyone. Okay, bye.
Thank you. Bye.
Bye.
Teacher.
Okay, bye. Welcome.